Welcome to Lecture 3B, second part of Lecture 3. As I mentioned in the first part, one of the main things that we look at in kinetics is reaction rates. How fast do reactions go? We looked at some of the factors that can control a reaction rate, but how do we actually measure a reaction rate? It's not like our beakers have a rateometer that tells us how fast a reaction is going. So we have to find some way of measuring the speed of a reaction. Well, what is a rate? Anytime we talk about the rate of something, we're generally relating some sort of progress per some unit time. A great expression of rate is our speed. Miles per hour, kilometers per hour, feet per second, meters per second, whichever system you use. It's always some distance per time. But we can use all kinds of things. It doesn't have to be a distance, but almost always it's per some unit time. So for a chemical reaction, the thing that we look at is what is the change in concentration with time. So we're usually looking at a change in molarity with time. So we look at how the concentration of either a reactant or a product is changing with time. Let's look at this reaction here, simple redox reaction. We've got two iron 3+ and a tin 2+, exchanging a couple of electrons, and the iron 3+ becomes iron 2+, and the tin 2+ becomes a tin 4+. Okay, very basic reaction, easy to see where everything is going. So let's look at the reaction. Let's say that we start the reaction and we take a sample after 38.5 seconds. So when we started the reaction, the concentration of iron 2+ right here, let me highlight that here. So concentration of iron 2+ right here, we see it's a product. And so generally we don't start with any product in our reaction. We only have reactants in our reaction. So the starting concentration of iron 2+ we can assume was 0 if we're not told that there's anything there. After 38.5 seconds, we take out a measurement, stick it in our analyzer, and we get a result. And we see that it now has a concentration of 0.0010 molar. So we've made some iron 2+. The reaction has progressed over that period of time. We can write the rate of iron 2+ formation as the change in Fe2+ concentration over the change in time. That delta symbol that we see there indicates change. Anytime we see that delta, we're going to say that that's change. So the change in the concentration of Fe2+ over time. To calculate that, we just use the formula, the concentration final minus the concentration initial on top. That gives us our change. The time final minus time initial on the bottom, and that gives us the change in time. So what we get is 0.001 divided by 38.5, and that gives us a reaction rate of 2.6 times 10 to the minus 5 molarity per second. Molarity per second sounds like a really strange unit, but remember, we're looking at the change in concentration per time, so that unit actually makes perfect sense. We can also express the rate as a disappearance of reactants. Okay? If we did that and we looked at the change in concentration of Fe3+ with respect to time, we see that we have a negative sign there. Why do we have a negative rate? Well, that's because the concentration of iron 3+ is going down. So the initial concentration would be higher than the final concentration. And since we do final minus initial to get that change, that's going to result in a negative number for the concentration change. Change in time is always going to be positive, and so the resulting negative divided by a positive will always give us a negative value. But notice, because of the stoichiometry of 1:1 between Fe2+ and Fe3+, the value of the rate is exactly the same. It's just different whether it's minus or plus, and that's because Fe2+ was appearing, that gives it a positive sign. Fe3+ was negative because it was disappearing. Other ways that people look at measuring rate over a particular time is they can graph concentrations of different reactants or products over time. They can get a slope. Remember, all the slope is rise over run. If you plot concentration versus time, that would give you a change in concentration over change in time, and that is a rate. So if you can get a slope at any one of these points here by taking a tangent, then you can get an instantaneous reaction rate. So there's lots of different ways of doing it. We will not be doing the graphical method. It's a little more difficult to do, but I could see some circumstances where it might be easier, but you don't have to worry about being able to do that on an exam or anything. So let's look at this idea of reaction rates. We saw that we have sign changes, whether we're referring to reactants or products. What if we had something with different stoichiometry? Well, that means that they get used up at a different rate, and so that means that those values would actually be different. So if somebody said, well, what's the rate of the reaction? You would have to say, with respect to what? And you would have to make sure that you measured it with respect to one of the things that relates to that. So what we want to be able to do is we want to find a way to express the rate of a reaction with just a single value. So it doesn't matter which reactant or which product we use, we are always going to get the exact same value to express the rate of a reaction. Turns out that we can use stoichiometry to accomplish this. Let's go back to this reaction here that we saw on that very first slide. 2Fe3 plus tin2 plus goes to Fe2 plus tin4 plus. Now, if we write out the rate of reaction for each one of these, we get something that looks like this. Now, this looks really complex because it looks like all one really big equation. It's actually 4 small equations with lots of equal sign in there. So this is 4 different ways to write the exact same rate equation. So what we do is notice that every one of them has a change in concentration over change in time. Okay, so what we then do is we take any coefficient and we make its reciprocal. Okay, notice that this is 1, so there's no 1 here. There's a 2 here, so that goes there. So it becomes an inverse reciprocal for any coefficient from the balanced reaction. Okay, so 2 becomes 1/2. If there were a 3, that would become 1/3. If you had a 6, that becomes 1/6. Okay, that takes care of the stoichiometric differences between the rates. Now we just have to deal with the pluses and minuses. So what we do is anywhere that we have the rate of change of a reactant, we put a negative sign in front of that. The reason we do that is because we know that the change in concentration of a reactant is going to be a negative value anyways, because the concentration of reactants are going down. So the numerator in a reactant rate change or concentration change would be negative, and the negative sign now that we put out in front changes that back into a positive. So we can say that rate is equal to -1/2 change in Fe3 plus over change in time, or we can say that it's equal to the negative change in tin2 plus over change in time, or it's equal to 1/2 of the change in Fe2 plus over time, or the change in tin4 plus over time. No matter which one of these concentrations we measure to get the rate, we will get the exact same value. So once again, we use inverse ratios of the balancing coefficients, and reactants would have a negative sign in front of them, and products have a positive sign in front of them. And that gives us always a positive value for the rate, and it means that no matter which reactant or product we use, we will always get the exact same value for the rate of the reaction. So let's consider this following reaction. A plus 3B goes to 2C plus 2D. So let's say we forgot to measure our concentration right when we started. It's probably 1 molar based on this information, but we can't really count on that since we didn't actually get its value. So after 2 minutes, somebody says, hey, what's the original concentration? The person goes, oh, I forgot to get it. So 2 minutes in, they take a sample and they measure it, and they find that it's 0.9986. That becomes our starting point at time equals 2 minutes, and that's fine. We have a starting time and we know what it is. It doesn't have to be 0. 2 works just fine. And then sometime later, 13.2 minutes later actually, we take another sample and we find that the concentration of B is now 0.9746. We want to know what is the average reaction rate during this time. And that's all we can get using these formulas is an average reaction rate as opposed to an instantaneous reaction rate right at a given time. So we can write out all of the different rate laws here, or rate expressions. We only need one of them. The one that we need is right here. And the reason we need that one is because we measured the concentration of B. We didn't measure A, C, or D, but if we did, we have the equations at our disposal to use them. But notice that A has no fraction in front of it, and that's because it has a coefficient of 1. Our B has a coefficient of negative 1/3 because 1, it's a reactant, and 2, it has a coefficient of 3, so 3 becomes 1/3. C and D have 1/2 in front of them because they have a coefficient of 2, and they are both positive because they are products, and so their change in concentration is already positive. So let's go ahead and use our equation for B. We have 0.9746 minus 0.9986. We use final minus initial, so we get a negative value for the concentration change because the concentration went down. And then we want to calculate our change in time. Our final time was 15.2. Our initial time was at 2 minutes, so we have 13.2 minutes. And now I just do negative 1/3, my change in concentration over change in time. And let me just write some parentheses in here because it doesn't look right. So it looks like 1 minus 0.0240 in a fraction. It's negative 1/3 times the change in concentration, which is negative 0.0240 over the change in time, 13.2 minutes. And we work all of that out, and we get 6.06 times 10 to the minus 4 molarity per minute. Now, you need to be very careful when you're working problems because you will have different time aspects given. Sometimes problems get sneaky. I try not to be sneaky, but every once in a while a problem goes by me where they give you a time in minutes and then they ask you for the rate in molarity per second. And so you would have to do a conversion factor between molarity per minute to molarity per second. And you can use unit analysis to do that, but you just need to make sure that you keep your eye on that. All right, that finishes out Lecture 3B, talking about reaction rates and how we calculate them. It's a little bit of a weird concept, especially writing out the different rate expressions for the different reactants and products. So if you have any questions on anything on here, make sure you contact me.